So starting into chapter 5, polynomial and rational functions. So we're getting a little more complex, starting with quadratic, which are a special case of polynomials, and going from there. So section 5.1 is going to be talking about polynomial functions, and we're going to first learn how to identify a polynomial function. And how to identify their degree. How do you tell the degree of a polynomial? And then we're going to graph polynomial functions using transformations. That's going to come in handy several times. And then identify the real zeros of a polynomial function and their multiplicity. So zeros of polynomial functions have a number associated with them called their multiplicity. And then we're going to analyze the graph of a polynomial function. And we're going to leave out the build cubic models from data. It'd be really interesting, but we just don't have time. So here's some examples of a linear function. Oh, any function that can be written as ax plus b. And then a quadratic function can be written as ax squared plus bx plus c. Well, if you want to let the function get longer and longer and longer, you're going to run out of alphabet letters. And so computer people have come up with this idea of the subscript of numbering the coefficients so that we don't run out, because we'll never run out of numbers. So the subscript 1 corresponds to the exponent 1 on the x, and that also works here. If you think about that x to the 0 equals 1, there could be an invisible x to the 0 there. So here in the quadratic, on the second degree term, the squared term, we have a subscript of 2. On the exponent of 1, we have a subscript of 1. So the subscript tells you what the exponent is on the x that it goes with. So a polynomial function in one variable, which is all we're going to focus on in this class, is a function of this form. And this is pretty formal math, but I want you to get used to reading that. This a sub 0 is the constant, so that would be like plus 2. Then a sub 1x means, oh, suppose I have a negative 3x term. And then I could have a 4x squared and a 5x cubed and a 7x to the 5th. Every term doesn't have to be there, right? So for this example, n is 5, because that's the highest exponent I'm seeing is a 5. So then a sub 5 is the number 7. So the a sub n and then a sub n minus 1. So this is n equals 5. The highest exponent I'm seeing is a 5. So then the fourth coefficient will be a 0. Third coefficient's a 5, and so on. So those are all constants, and they're called the coefficients of the polynomial. N has to be greater than or equal to 0, and has to be an integer in order to be a polynomial, and x is the variable. As long as the a sub n at the front isn't a 0, it's called the leading coefficient. So when we organize the terms in order by the exponents on the x, then the first coefficient is called the leading coefficient. And n is called the degree of the polynomial. So the exponent on the highest power of x, so this polynomial that I wrote here is degree 5. And again, the domain of polynomial functions, all real numbers. So here are some examples of polynomial functions. f of x equals 3x cubed minus 5x squared plus 2x. Doesn't have to have a constant, right? You could have f of x equals x minus 2. Oh, that's a really simple polynomial, but it's a polynomial. It meets the requirements. G of x equals 7 is a polynomial. All it has is an a sub 0, but that's all you need. So the idea of a polynomial might be a little bigger than you have in your mind right now, so stretch it to fit. Then examples of functions that are not polynomials. If you have a fraction exponent, or if you have a negative exponent, those are not polynomials. Their graphs are very different looking. So we're going to be just talking about polynomials. Each polynomial is a sum of monomials that are called terms. So each monomial that's a part of the polynomial is called a term. When the terms are put in order of degree, descending, so the highest one first, the first term is called the leading term. So as we read from left to right, it's the first one we come into. And this order is called standard form. If a term has a coefficient of 0, we omit it, save ourselves some writing. And if a coefficient is a 1, you will not see it either. The constant term is a sub 0. If all the terms of the polynomial function are 0, then that's a special creature called the zero polynomial, which has no degree. Because if I have this polynomial that's just a constant, this is degree 0, so that already got used up. So the zero polynomial has no degree. So here's a little summary of the properties of the graphs of polynomials. So we know the zero function is just the x-axis. The constant function is a horizontal line. Linear functions make lines, and quadratic functions make parabolas. So we've learned about all of those already. So the graph of every polynomial function has some special features. Every single one will be smooth and continuous. So A is a picture of a graph of a polynomial, and B is a picture of a graph that there's no possible way it could be a polynomial because it has corners and gaps and holes and all kinds of problems. So a polynomial function can be broken down into its individual terms and analyzed. And each term is an example of a particular type of function called a power function. And when I first learned about these, I wondered why were they so powerful? I didn't understand that they're called power functions because of the exponent on them. So our power function of degree n is a monomial function of the form f of x equals a x to the n. So it has only one term, it's a monomial. A is a real number that's not 0, otherwise we're at the boring case, the 0 polynomial. And n has to be positive, and in fact has to be an integer, or it's not a power function. So f of x equals 2x cubed is a power function. G of x equals negative 3x to the 5th is a power function. But if I have h of x equals 3x to the negative 2, that's not a power function because it has a negative exponent. And p of x equals 2x to the 1/2 is not a power function because of the fraction exponent. So if n equals 2, we already know we have a parabola with the vertex hk, and we know what those parabolas look like if we don't have any shifts. So the vertex is 0, 0. In fact, if we have f of x equals ax squared, then we know the vertex is 0, 0. And we know what effect a has on the graph. If a is positive, it opens upward. A is negative, it opens downward. And then we also know about the fatter and thinner parabolas. So now we're going to graph n equals 4 and n equals 6 and n equals x. So we're going to start with f of x equals ax squared. Let's just start with plain x squared. Then let's do g of x is x to the 4th. H of x is x to the 6th. And k of x is x to the 8th. And we'll look at those and see what we notice and fill in these properties of a power function. So they're going to be different for even and odd. So this is the properties of power functions, x to the n. If n is a positive, even integer. Okay, and we'll see what we notice about the graph. Okay, then we'll also look at power functions where n is odd, beginning with x cubed, and then we'll graph x to the 5th and x to the 7th, and I hope you'll do this along with me using Desmos. And then we'll look and see what happens when we have a positive odd integer as the power on the power function, and what are the features of the graph. So all of the transformations that we've worked on so far can be applied to power functions. So you can see that this is to the 5th power graph, so it's going to look like the power function, but the -1 is going to shift 1 unit right. Then the function's happening. Then outside of the function you have a 1/2. So that's going to be a vertical compression by a factor of 1/2. Every y value will be half as large as it was. And then you're going to shift down 2. So we'll do this other one, the second one in class together. And now we're going to look some at graphs of polynomial functions. And let's talk about some of the features. So at every x-intercept, the graph has to either cross or touch the x-axis. That's the meaning of an x-intercept. And to find x-intercepts, we set y equal to 0. So we say f of x equals 0, solve for x. That's how we find x-intercepts. So that means the x-intercepts of the graph of the function are the same thing as the zeros of the polynomial function. So these dots can be called x-intercepts of the graph, but they're also the zeros of the function. So those words really are interchangeable as far as their meaning, but they're used in different contexts. Zeros of a function and x-intercepts of a graph. So if f is a function and r is a real number, that when I put r into the function I get 0, then r is called a real zero of f, and we can also see that it's an x-intercept of the graph. So these are equivalent statements, and what I want you to do next is copy these 4 equivalent statements. Studies have shown that writing in your own handwriting, and especially if you're also saying it aloud at the same time, is a really great way to remember important things. And this is super important.